Hello everyone, welcome to Power Electronics lecture number 2. Today we are going to discuss about power diode and SCR. So let's begin with the power diode. Now what makes a power diode different or unique in comparison to a rectifier diode? So let's talk about a rectifier diode. Your rectifier diode supports lower rating. That means the wattage rating of a rectifier diode is quite low. So we have a lower rating around 100 watts. Whereas for a power diode, the ratings are in the range of, we have a voltage rating in the range of 2 kilowatt, 2 kilovolt. Current we have from 1000 to 1500 amperes, and the wattage rating is somewhere around 3 kilowatt to 5 kilowatt. Now the symbol wise, the power diode has the same symbol as a normal rectifier diode. It has an anode marked as A, cathode as K. The voltage across the diode can be marked as VAK, anode to cathode voltage, and the current flowing through the diode can be termed as IAK, anode to cathode current. Alright, now let's talk about the characteristics of diode. So let's first talk about a real IV characteristics of a diode. So a diode will have characteristics which looks like this. This is IAK, anode to cathode current, VAK, and in the forward characteristics, when voltage is positive, current is also rising exponentially with it. So we have a characteristics which looking like this. And in the reverse bias, the current is very small. Okay, we have a reverse saturation current till that range. So let me draw over here. The current is very small, almost on the x-axis, and then once the reverse breakdown has reached, it will sharply increase. Okay, so that's the IV characteristics of a real IV characteristics of a normal rectifier diode. So this is my real IV curve. All right. Now the forward voltage, the diode takes around zero point 0.7 volts to turn on, and after that the current starts increasing exponentially. So this is around 0.7 volt, and this voltage is called as the VD on voltage of the diode. So once the external applied voltage crosses the VD on voltage of 0.7, the diode starts conducting. Over here, this value might be around, let's say, minus 10, and it can reach, there is a break over here indicate that there can be a change in the range. So this will be around minus 100 volt. Alright, so once the reverse voltage VAK reaches minus 100 volt, normally for a normal diode, it's enter into the breakdown region, normally avalanche breakdown. Now compared to this, we also draw IV characteristics, ideal IV characteristics of the diode. So let's see how the ideal IV characteristics look like. So let's draw the axis. This is VAF, and this is the anode to cathode current graph. Now in case of a ideal diode, we consider when the diode is on, the voltage drop across the diode is almost like non-existent, that is zero. So we consider whenever the voltage VAK is positive, the diode is forward biased and it starts conducting. So it's ideally it is looking like this. So this is when the diode D is on. Alright. And when the diode is off, it is represented by a line parallel to the x-axis on the negative x-axis over here. Alright. So this is what happens when the diode is off. The more and more voltage you apply, still the current won't increase, and that's what makes the diode unidirectional device, right? This arrow over here indicates that the current cannot flow from cathode to anode. All right, so this is the normal IV curve, ideal IV curve for a normal rectifier diode. Ideal IV characteristics of diode. Now, when we talk about power diode, the ratings will change slightly. So over here we can write ratings of around, let's say, minus 1000 volt. The reverse breakdown voltage can go to minus 1000. Here this VD on voltage might go to around, let's say, 1 to 2 volt. Alright. But in case of realistic scenario, when we apply input voltage in case of power application, the input voltage itself is pretty large. Let's say the input voltage is around in the range of 230 volts in a single phase supply, and it's in the range of, this is single phase, and it's in the range of 440 to 450 volts in a three phase supply. So such a high value of AC signal, right? We are talking about the AC signal. Okay, repetitive periodic sinusoidal signal is the AC signal. So this can be single phase or it can be a three phase signal. So in this case, since the input is quite large, this 0.7 volts drop can be neglected in case of a rectifier diode. Now in case of a power diode, the VD on voltage drop is still less. It's around 1 to 2 volt. So still it can be neglected. It's very small compared to 230 volts. Alright. So that's why your ideal diode model is preferred. So this is ideal diode I-V characteristics will be valid for power diode also. So this is, I mean, we can explain the working of a power diode with the help of this characteristics very well. Alright. So what happens when the diode is on? When the diode is on, it will behave as if it is like a open circuit. So let me show it to you. When the diode is on, it will behave as a short circuit, and when the diode is off, it will behave as an open circuit. Alright. And when it is behaving as a short circuit, that means your VD on is considered to be assumed to be 0. Alright. So that's what the ideal diode will do. So if you see carefully, it has only two states. Diode is on or off. Now this is resembling the behavior of a switch. Alright. The switch is, this is my switch. This is my second switch. The switch is fully on or fully off. Alright. So that's why we say that your ideal I-V characteristics of the diode represents the characteristics of an ideal switch also. So it represents the characteristics of an ideal switch also. Alright. Now let's see whether this switch is controllable or uncontrollable. Now I hope you have understood why we go for a ideal power diode. The reason being, for the input is quite large and the VD on drop is quite low. So this drop can be neglected as compared to these input voltages. That's why we go for a ideal power diode characteristics also. Alright. Now next is we will study about AC and DC signal. So yeah, let's talk about we have learned about the full wave rectifier. We have learned about the full wave rectifier in literature. So what's the output waveform for a full wave rectifier? So the output waveform for a full wave rectifier looks something like this. This is my V out, and the full wave rectifier will have a characteristics looking like this. For positive half cycle, it's following the input. For negative half cycle, it's following the negative of input. Again for the positive half cycle, again for the negative half cycle. So this is my output characteristics of, or output waveform with respect to time of a full wave rectifier. So this is my full wave rectifier output waveform. Alright. Now about this output waveform, let's say my input voltage over here is, input voltage which is applied to the rectifier is around 230 volts and 50 hertz. Alright. So I'll draw the input waveform. I mean, it's 230 volts is quite large, but I am drawing it which will fit the scale over here. So this is my V in. Okay. Now if I calculate the average value, I mean, if I want to know now this V out is a AC signal or a DC signal or something else. So whether input is a AC signal or no, yes, it is a AC signal. Now what's the mathematical definition of a AC signal? Any signal is a AC signal which should be periodic and its average value should be 0. So if I see the average value, V in average, if I want to find the average value of this input AC signal, sinusoidal signal, its value is 0. So mathematically, any signal's value which is periodic signal, its average value is 0, that can be categorized as a AC signal. Now a full wave rectifier has a job of converting AC signal into DC signal. But the waveform which you see over here, whether it is a AC or a DC signal, so think about it. Okay, it may, the first opinion will be it looking like a AC signal, but no. You see, mathematically, the average value of this waveform is not 0. So what is the average value of this waveform? Since our entire waveform is on the positive side, the average value will be somewhere around here. Alright, and the average value is positive. This is my average value, and this is a positive quantity. So it's not 0, so it's not a AC signal at all. Alright. But what is this value? It reaches a peak value of Vm. Okay. So what is this peak value given by? This is Vm. So what is the relation between Vm and Vrms? This is the RMS value, 230 volts. This is my RMS value. So my peak value Vm will be Vrms into root 2. So that will be 230 into root 2. So this value over here, Vm, is basically 230 root 2. So it's a quite large number, in fact. Okay, 230 into 1.414. So greater than 300 volts it will be. All right, and yeah. So coming back to the question whether this waveform is a AC waveform or a DC waveform. Now, if you see carefully, this part over here, which is the average value, this is my DC signal. This is my DC component. So this is my DC component in the AC waveform. And what is my AC component? This entire Vm is my AC component. This is the AC component. So that means we have a signal which contains both AC and DC component, and that is termed as a pulsating DC. Okay, so full wave rectifier converts a pure AC signal into a pulsating DC signal. So this is called as a pulsating DC signal. Alright. Now, mathematically we can also say that its V out average value is not equal to 0, and its RMS value is also not equal to 0. RMS is the root mean square value, and that is also not equal to 0. In fact, both of them are positive. Alright. Now let's give let me give you another scenario to distinguish between AC and a DC signal, and a signal which is containing both AC and DC. So let's consider this waveform. Let's consider this waveform. So we have, I have a situation wherein the waveform is looking like this. Okay, let me draw the sinusoidal signal a little more properly. Alright. So this is my some random waveform which is coming up. Some device is giving this circuit output is this. So what is this waveform looking like? It's a AC signal or a DC signal? Definitely not a DC signal. Definitely not a AC signal alone. But this much, this is the DC quantity. So this much is my DC component. And what is my AC component? AC component is from year to year. So this is again a pulsating DC signal. Alright. Its average value is not equal to 0. So the average value, V average, is not equal to 0. So that cancels out that it's a AC signal, and it has a DC average value, and this DC average value will remain same. So let's say this is 5 volt. So the average value of this signal will be always 5 volt. All right. So yeah, I hope the distinguish between the AC and the DC signal is clear. All right. So what is the learning from this power diode? What we learn from this power diode? All right. So let us write the learning curve from this power diode. What we learn from the power diode is that the power diode behaves as an uncontrolled switch. power diode behaves as a uncontrolled switch. Now, what do you mean by uncontrolled switch? Uncontrolled switch means its conduction, that is on or off, turning on and off, cannot be controlled. Okay, so we can simply write over here, we don't have we don't have an control over its conduction period. We don't have a control over its conduction. So let me explain you with an example. Let's take a half wave rectifier circuit and let's apply a power diode to it. So power diode behaves as an uncontrolled switch. That's the learning which we have to prove over here. Alright. So let's begin with an example. Let's quickly draw a half wave rectifier circuit. So half wave rectifier circuit will have a AC input, will have one rectifier, alright, and a resistor. Let's say this input is 230 volts 50 hertz single phase supply. This is V in, this is my diode D1, and this is my resistor which is around 10 ohms, let's say. And we have to measure the output across the resistor, which is the load resistor. This is plus or minus V out. Alright, now we have to adopt a ideal diode strategy over here. So that means whenever the input voltage is positive, the diode will be on. Whenever the input voltage is going negative, the diode will be off. Simple as that. Alright, so let me draw the input output waveform for this diode. So let me draw input waveform as a dotted line. So this is my input waveform. This dotted line, black color line is my input waveform with respect to time. Now let me draw the output waveform. Now, in case the diode is on, when it is on during the positive half cycle, remember this is a AC signal. So it will go to positive half cycle and negative half cycle also. This is my V in. Let's consider. Alright. So during the positive half cycle, the diode is on. In fact, whenever the voltage V in is greater than 0, it's the diode will be on. Okay. So we can say, and when the diode is on, what will happen to the output? So let's consider this now in this scenario. So when the diode is on, diode D1 is on during entire period of positive half cycle, during the entire period of positive half cycle. Alright. Now when we draw the circuit of this in the entire period of positive half cycle, so let me draw, the diode will behave as, when the diode is on, it will behave as a short circuit. Alright. So let us replace the diode with a short circuit and let us draw this resistor. Now in this situation we have to find out how much is my value of V out. So this is my V in which is applied and this is my V out. Now as you can see, the diode is short circuited, replaced with the short, and this is my resistor R1. So here we can say output is equal to V in. That means output voltage will follow as it is the input voltage. Okay, the output is following the input over here in this case. Okay, and this is what happens during the entire period of positive half cycle. So how will be my waveform now? My waveform will look like this. Half wave rectifier, as we already know, this is the waveform. Alright. Now let's see what happens. This is why I'm plotting the output, V out value. Now let's see what happened when the negative half cycle appears. So whenever the negative half cycle appears, the voltage across the diode becomes negative, and as soon as the voltage across the diode D1 is negative, it's off. It becomes off. So diode remains on during the entire period of positive half cycle. That's more important. That means we cannot even turn it on at some particular period. Let's say we want to turn it on over here. It cannot be turned on, right? This is pi, 2 pi, and 3 pi. So we cannot control its conduction turn on period. Okay. So yeah, during turn on, the turning on of the diode is uncontrollable. Okay. So it's uncontrollable. Okay. The turning on, the uncontrolled turning on of diode D1 is uncontrollable in this case. Okay, we cannot control, once it turns on, we cannot turn it off at will, right? Once it turns on, it remains on unless the condition is satisfied. So that is during the entire positive half cycle. During this entire cycle, the diode turns on. We have no control whatsoever over it. All right. Now, in the second condition, during the negative half cycle, diode D1 is off, and that happens during entire period of negative half cycle. So when this happens, the diode is off, means it will behave as a open switch. All right. So let me redraw the circuit in this case. So it will behave as an open switch. Positive, negative. This is R1, and I have V in over here. So it is, since it is open circuit, no current flows through it. So this I is 0. So whenever there is no current flowing through the through the resistor, the voltage drop across will be 0. Okay, so voltage drop across the output will be 0 in this case. All right, so here I will draw the waveform now for a negative half cycle. So output waveform is 0. All right, and in such a case, again, since it's a periodic signal, this thing will repeat again during the positive half cycle. Again it will become follow the output will follow the input, and again during next half cycle, again it will become 0. So this is my output of a half wave rectifier. This is half wave rectifier output. Okay, all right. So in this period also, when the diode remains off during the entire period of negative half cycle, so there is no control parameter over here. Once it's off, it will remain off until the condition is met. All right, so again, the turning off of the diode is uncontrollable. Okay, so from here we say that turning off of diode D1 is uncontrollable. So both the cases, the turning on of the diode is uncontrollable, the turning off of the diode is uncontrollable. That's why we say that in the learning that the power diode behaves as a uncontrolled switch. All right, that's what it proves the point that your power diode is working as a uncontrolled switch. So why switch? Because when it is on, it is behave as an open switch, closed switch. Sorry, closed switch. So here we can say the switch is on, fully on, and when the diode is off, the switch is open. So we can say the switch is off. All right. Therefore, it works as a therefore power diode can behave as an uncontrolled switch. All right, and that gives rise to another power device. Now, this is one of the power device. All of course, its applications are limited. They are there. I mean, we often use power diodes in most of the power applications, but it has, due to its high voltage rating, power rating, and the current rating. But definitely, it's there for some applications of power electronics. All right. So that gives rise to a new power device, that is SCR. SCR stands for silicon controlled rectifier. Silicon controlled rectifier, and that's the second power device which we are going to study. Why we are doing this? Why we are going for another power device? Because power diode behave as an uncontrolled switch. We want to establish some control over when the power device will turn on And if such thing happens, that is possible in case of a SCR, silicon controlled rectifier. So let's dive into it directly. Now, without explaining you in detail about the silicon SCR, silicon control rectifier, we'll study its ideal behavior, and we'll proceed with the further syllabus. All right, I will let you know why we can go ahead with it. So, a symbol of a SCR is similar to a power diode. So, it has a anode, then it has a cathode, and it has a third terminal also, which is the gate terminal. So, this is my gate. All right. So symbolically, if you want to represent, its anode is denoted by A, cathode denoted by K, and gate denoted by G. So gate is the control terminal. All right. So this is my SCR symbol. Now if I want to represent the voltage across anode and cathode, it's simply represented as follows: VAK, voltage across anode to cathode, and the current which flows through this device can be denoted like this. This is IAK, or we can also call it as IA. Now, this gate terminal is also significantly important. We apply some gate train pulses, a gate pulse, so that the diode conducts. We'll see that shortly. So we can apply this gate. It's valid to show this gate current also flowing into the gate terminal. All right. Now this VAK can also be written as voltage across the SCR, so we can write VSCR, and this IAK can also be denoted by IA, or anode current. So this is anode to cathode voltage, or voltage across the SCR, and this is around anode current, or we can call it as a anode to cathode current. It's normally this is preferred, IA is preferred, and VSCR or VAK is also preferred. Okay, so this is about the symbol of the SCR, that is silicon control rectifier. Now let's dive into its ideal behavior, because we will shortly know now why the ideal behavior is preferred. So let's draw the ideal IV characteristics of SCR. So here we can write IA, here we can write VAK, anode to cathode voltage. Now listen, this is very important, so let's mark it together. So this first characteristics is similar to the reverse blocking mode characteristics of a diode, but in the positive x-axis. So this is region number 1, okay, and in this region number 1 we denote it as a forward blocking mode of SCR. All right, we have not studied it, but we are just explaining its behavior ideally, and this will help us to understand the SCR device very well. All right, so in case of a forward blocking case, SCR is off. Okay, just wait a second. So in case of a forward blocking, the SCR is off, and it will behave as an open circuit. In second case, second region of operation is over here, and this region of operation we call it as a forward conduction mode. Here my SCR turns on, forward conduction, and here my SCR is on. And when my SCR is on, it will behave as a short circuit. It will behave as a short circuit. Now there is a third region of operation also for the SCR. So in case of a third region of operation, we have over here this, we term it as 3, region number 3, and this we call it as a reverse blocking mode. Reverse blocking mode of SCR. And here also SCR is off. and whenever SCR is off, it will behave as an open circuit. Okay, and this entire characteristics is called as ideal IV characteristics or ID curve of SCR. So kindly make a note of it. We have just started describing the behavior of SCR in terms of its turning on off. All right, because we this is all SCR can also behave as a switch. All right. So we'll not talk about the practical IV characteristics right now. We'll talk about the ideal IV characteristics and proceed. And there is a reason for it, because in case of SCR also, the input supply voltages, the V in voltages are very high. 230 volts for single phase and 440 volts to 450 volts for a three phase supply. So in these situations, the forward voltage drop when the SCR is on, it's around very small. So it can be neglected. That's why dealing with the ideal IV characteristics, it's very relevant. All right. So in case of region number one, uh, we keep on applying the forward voltage VAK positive, but there is no current. So SCR is off. In region number two, even for a positive value of VAK, the current starts shooting up. So that is the forward conduction state, and the voltage drop across the SCR over here is zero. And in case of third case, the SCR, the voltage across anode and cathode is negative. You go on increasing it, still the SCR will be remaining off, remaining in the off state. All right. Now let me just give you a glimpse of a real IV characteristics of SCR, and let's see how closely we resemble the ideal IV characteristics. So this is my, let's say, IA. Current is in the y-axis always. Voltage is in the x-axis. And let me draw the IV characteristics over here. All right. So in case of SCR, the IV characteristics look something like this. This is my region number one. This is my region number two. It's slightly bent. Let me draw it. Yeah. And this is my region number three. Region number 3 is almost on the x-axis until a breakdown voltage is reached, and then it suddenly starts shooting up. The current starts shooting up when the breakdown region is reached. Now this we have not discussed. This is region number 4, which we have not shown over here. Alright, it's not necessary. We do not operate SCR uh, in the reverse, not in the reverse braking mode. It's a breakdown region. Region number 4 is the breakdown region. We never ever operate it over here. And its value is very high. It's in the 1000 volts. So its value is around more than 1500 volts. So we never operate it over here, so we will not talk about that. So this is the breakdown region. All right. When we go from, let me show you the forward conduction region. This is my forward blocking region. This is my forward conduction region, and this is my reverse blocking region. This is 1, 2, and 3. All right. The resemblance you can see over here. We are talking about a power device, right? So the current will be in amperes and voltage will be in volts, few hundreds of volts, right? So when we talk about region number one, in case of ideal and real IV characteristics, what happens is you go on increasing the value of VAK, and there is hardly any current IA. The anode current is very small in milliamperes, and so that's why we have shown it on the x-axis over here in case of ideal IV characteristics. Now when the SCR conducts, the voltage drop across the SCR is very small. So this voltage drop I'm talking about, this is usually around 1 to 2 volt, and compared to the actual input AC voltages, that is 230 to 440 volts. In case of single phase and three phase voltages, 1 volt or 2 volt is very small, hence it can be neglected. So the SCR voltage drop when it is on, it's neglected. That's why this line is drawn over here on parallel to the y-axis. All right, so SCR is on, it will simply behave as a short circuit. And in the reverse blocking mode, as we apply a negative voltage across the anode and the cathode, the SCR, the current flowing through the SCR is very small, and here it depicts the behavior equally well. And once we reach a breakdown value, we never really operate in a breakdown region, because that is irreversible process. It will damage the SCR. So that's why we don't discuss about the breakdown region over here right now for initial working. So this is my real IV curve of SCR. And for few lectures, we will be only talking about, in fact, the entire AC to DC converter. We will be following your ideal IV characteristics easily. We'll be talking about ideal IV curve for the SCR. Using this nature of the graph, we can explain the behavior of SCR very easily. Alright. Now, let's see how SCR is a controlled switch. Now, one important thing to notice, there is some condition. There are two conditions to turn on the SCR. So we will write together. In order to turn on the SCR, we have two conditions. Write down. SCR has to be biased. SCR is to be operated in the forward blocking mode. SCR has to be operated in the forward blocking mode. So first of all, we have to apply a positive VAK voltage, right? Secondly, positive output voltage means we have to apply a positive VAK voltage, VAK positive. Alright. Second case, your gate trigger pulse must be applied. Second condition is your gate trigger signal or pulse must be applied. So both the conditions are necessity. Only one condition will not, prove it to be on, and this gate trigger pulse must be positive. Must be applied for positive values of V in. For positive values of V in. Whether V in is AC or DC, it's irrelevant. It should be positive value. So for a positive value of V in, the gate signal trigger pulse will be applied, and this gate trigger pulse is of this nature. You have one pulse and that's it. That will turn on the SCR. Help running on the SCR. Alright. So this is my IG, which we have shown in the symbol invert. Going into the terminal of gate over here, this is the gate trigger pulse. So the two conditions for turning on the SCR are SCR should be biased in the forward blocking mode, and second condition is the gate trigger pulse must be applied. So that is what the positive values of V in. Alright. Now let's consider simple scenario over here with input DC supply, and let's try to simulate the behavior of the SCR. Okay. So let me consider this circuit. I have a DC input, I have a resistor, and then I have a SCR. SCR can be identified with its symbol. So this is my SCR symbol. Let me mark this is RS. Let's say my input voltage is a DC signal, and the value of the DC signal is around 500 volt. Alright. This is my voltage across the SCR VAK. This is my gate. Okay. And let's say I have applied my gate trigger. So I am representing in the form of IG. Now remember this gate signal or a gate current over here. It's a very low magnitude, right? It's in milliamperes. It's not in amperes. Whereas the current flowing through the circuit, that is IA, the anode to cathode current, let me call it IA, that is in amperes. Okay. So we have to distinguish between them. Your IA is in the range of amperes, and IG, the gate trigger pulse, is in the range of milliamperes. So this is very, very important to understand. All right. Now as we saw the gate signal should be like this, right? This is my gate current signal. All right. Let me draw. Now let us try to understand the behavior of the circuit with the help of waveforms. So let me first draw IG. So we know how the IG will look like. It's a trigger. It's a one time pulse. So let's say we can control where it can, where it will start. We can start directly at 0 also, but let us say that we have delayed it quite a bit over here. All right. So let that delay can be called as alpha. Okay. And this is time. Let's say it is alpha. You can consider a number also, but it's fine. Um, you can consider alpha as few seconds also. Now our task is to plot voltage across the SCR, that is VAK, and current flowing in the circuit, that is IA. Alright, I hope that this is understood. We have to plot the voltage across the SCR and the current flowing to the SCR or the circuit. So let's just think about it. Alright, so we have applied DC input voltage. So during the, there is only DC input means what? It will be something like this. This will remain 500 volts throughout. This is my V in. Irrespective of anything, this value will be 500. Today it's 500, tomorrow after 1 year also it remains 500, let's say. So we have a DC input of constant value of 500 volt. Now how does the SCR works? So there are two conditions, right? Whenever we apply a 500 volts over here, let's say small current flows to the circuit and VAK is positive. But just VAK being positive is not enough. Alright. So if VAK is just positive and we apply just V in as 500 volt, the SCR still is turned off. Alright. So when SCR is off, it will behave as a closed circuit. Alright. So let's draw it. So this is what happens when SCR is off. So this is V in, this is plus minus VAK, and this is your resistor RS. Now what will be the voltage across VAK over here? The VAK voltage will be same as V in. Alright. Let's say from 0 to alpha. We have not turned it on. Let me plot it over here. And let me also draw the current relevant to this. Okay. So my VAK voltage will be similar to V in. So in this case, VAK will be same as V in. Why? This happens because SCR is not turned on. There are two conditions to be met. Only the forward bias condition is met, or the forward blocking condition is met. Sorry. When VAK is positive, the SCR is in the forward blocking state, and whenever SCR is in the forward blocking state, it's considered to be off. You can say SCR is off, as you can see, and it's replaced by open circuit. So here we can say SCR is off. Hence it is replaced with open circuit. Now, what about the current flowing? When the SCR is off, the current flowing to the circuit will be 0. So, till 0 to alpha, that means until we have applied the trigger pulse. What about the waveform over here? Let me draw it. So the signal over here will be, it will be constant equal to V in. So this is 500 volt. Alright. And the current will be 0. Let me draw the current in blue color. So the current will be 0 till alpha. Now what happens? This is before, this situation is before IG, before the trigger pulse. Okay, the SCR remains off over here, and VAK, anode to cathode voltage, is V in, and the current is 0. All right, this is clear. Now what happens once we apply gate current? So after application of gate current, after IG applied, so once we apply the gate current, the SCR turns on because it's already in the forward blocking state. VAK is positive because we have applied V in over here. So IA starts flowing now. So how does the circuit will look like? The circuit will look like this. The SCR turns on and it will behave as a short circuit. Alright. So here the SCR is on. Alright. This is my V in. This is RS. So what about the VAK voltage over here? Anode to cathode voltage. Now since it's a short circuit, it will be 0. But will the current be 0? No. The current will flow in the circuit. So what will be the current value? As you can see, this is a short circuit. Current is basically V in upon RS. Alright. And let's say the RS value is around 5 ohms given to you. So V in is around 500 and RS is 5. So IA will be around 100 amperes. Alright. So that is what we will get. The VAK will become 0, will drop to 0 because the SCR is on over here. And it will remain off until we have a next trigger pulse. Okay, your this will be 0. and whereas your current will be around 100 amperes. I've explained why 100 amperes. So this will be around 100 amperes. Here is the reason for it. All right. So this is the behavior of the circuit, which will follow after application of trigger pulses. So once both the conditions are met, that is VAK is positive, that is in the forward blocking mode, and the gate trigger is applied, the SCR turns on. And once it turns on, the voltage across the SCR is very small, it's zero, and the current starts flowing across it. Alright, so this is the behavior. So we can easily depict over here. Here the SCR is off, and here the SCR is on. Alright, so this is the behavior of SCR in case we apply a pure DC signal. Alright, now let us see another scenario. I hope this is clear. Let us see just one more scenario over here. Let's consider that the SCR which we have shown over here in the previous circuit, it's reverse. So this is next scenario. We have applied a constant DC value. We have a RS of 5 ohms, let's say, and we have applied a SCR like this. This is my SCR. The forward voltage across the SCR VAK is like this, positive to negative. Alright, and this is my V in, which is 500 volt, and let's see whether the current will flow or no in this condition. Let's say we also apply a trigger pulse here also. Alright, so let's plot your IG characteristics again, your IG curve, then the VAK waveform, and finally versus time, the current which should flow. Okay, which should flow in the circuit. Alright, let me draw it properly. The current which should flow in the circuit. Alright, so that is IA. This is VAK. So let's apply a trigger pulse after a delay. So let's say this is my trigger pulse. This is IG. Okay, let me draw it again. So this is my trigger signal. It remains off and it's on for a very short duration. So this is my IG. With respect to this, we have to draw the waveforms for voltage across the SCR, anode to cathode voltage, and the current flowing through the SCR. Alright, so let's see this behavior. So when we have a SCR reverse connected in the reverse direction like this, V in will be negatively applied to the SCR. So basically SCR will remain in the reverse blocking mode. Whenever SCR is in the reverse blocking mode, the SCR is off. It will not conduct at all. And we have seen when the SCR is off, the voltage across the SCR is, here the voltage will be V in. In this case, it will be minus V in because the voltage across the SCR is reverse, right? So here, in this case, your VAK will remain minus V in before the IG pulse is applied. Okay, so here the value of, let me draw this a little more carefully, like this, let's say. So here the value of VAK will be negative from here to here, and this is minus 500 volt. Here it will be minus 500 volt. Alright, what about the current? When the SCR is off, we have seen over here, it is replaced by open circuit. So the current IA will be 0. So the current over here, IA, will be 0. Let me draw in green color. This will be 0. Alright, so current IA is 0. Now what happens when IG is applied? Now even if we apply the IG, the gate trigger, still the first condition is not met. That is, the SCR is not in the forward blocking mode. It's in the reverse blocking mode. Alright, and if it remains in the reverse blocking mode, the same condition will persist. Alright, so even after the application of this pulse, gate pulse or a gate trigger pulse, your SCR will remain at minus 500 volt only until you have another pulse applied. Still the condition will remain same. Alright, and why this is happening? Because SCR is in the forward reverse blocking mode. Until it mode changes of the SCR, the behavior won't change. It will remain at minus 500 volt. Similarly, since the SCR is off, the current won't flow and the anode current will remain at 0. So this will remain at 0 amperes only. So this is the graph. This is the plots of VAK and IA versus time. I hope this is clear. So this will explain the application of characteristics of the SCR. Alright, and we can say that how we can control the on time of the SCR. Now in the previous example, we chose to control when to turn on the SCR. Alright, if we could have turned on much earlier, it would have turned on over here. Alright, so that means turning on of the SCR is controllable. Alright, and so that's the learning over here. Let us write it down. That's the learning which we learned from the above discussion. And what is the learning? SCR behaves as a semi-controlled switch. Now talk about why semi-controlled just short while from now. It behaves as a semi-controlled switch. That means its turning on is controllable. Turning on of SCR is controllable, and we will see in few lectures from now. We'll see about that. Its turning off is not controllable, so it makes its own decision, just like a diode, to turn off. So we can say turning off of SCR is uncontrollable. So that's why it's called as a semi-controlled switch. Alright, turning on is controllable, but turning off of SCR is very, very difficult. Okay, but it's and obviously it will turn off on its own once the condition is met. Okay, so that's the learning from the above discussion what we had for few minutes before. Alright, now let's go to the next topic, that is the power diode. Let's compare. So far we have discussed about the power diode, we have discussed about the SCR. Let's compare about the power diode and SCR. Alright, so in one column we have power diode, another column we have SCR, and we have few parameters which we had right over here, and we'll tick mark them one by one. Alright, so let's talk about it. Let's start. One of the parameters is controlled on, T on. Controlled turn on. Next parameter, let us write all the parameters. Controlled turn off. Then continuous gate signal requirement. This is the third parameter. Then we'll talk about bidirectional current capability. We are comparing power diode with SCR. And the fifth is which draw its symbol at the end. Alright, so let's talk about the parameter one by one. So in case of a power diode, is the turn on controllable? No. In case of SCR, is the turn on controllable? Yes. In case of power diode, we cannot even turn off the diode properly. It makes its own decision. So this is not controllable. But in case of SCR, also its turn off is uncontrollable. It's very very difficult to turn off an SCR. Whether there is a gate continuous gate requirement over here, in a power diode there is no gate, so no such requirement. And in case of SCR, there is no continuous gate signal requirement. In fact, we apply just a short pulse and that's it, it will turn on the SCR. So this is the gate requirement, gate trigger requirement for SCR, just a short pulse, nothing else. It's not a continuous gate requirement. We don't have to apply continuously the gate current. You apply this once and that's it, the SCR turns on. Whether we have a bidirectional current capability in power diode? No. Whether we have it in SCR? No. And why no? Because both are unidirectional devices. Let me draw its symbol now. So yeah, this is my A, K, this is VAK, and this is my current flow in one direction. Whereas my symbol for SCR will looks like this. It will have the third gate terminal, gate, this is anode, cathode, plus minus VAK voltage across the SCR, and currents also flows from anode to cathode alone. So both are unidirectional devices. Okay, and their current capability, it's very high. It's in the range of few hundreds of amperes. Its voltage rating capacity is very high. Okay, now what about the ratings of the power diode and the CR? Which one will have a higher rating? So in the literature it's given that, and practically also we can check the data sheets. The power diode will have a higher rating. Power rating, voltage rating, and current rating are higher as compared to SCR. Okay, so yeah, so that is what we have, and that's the last topic of discussion. And this is what we have, all we have for from this topic. Next time we'll start with SCR rectifier topic. So until then, let's revise what we have studied so far. So we have seen at the start that power diode act as an uncontrolled switch, okay, and SCR acts as a semi-controlled switch. We have seen a few examples wherein we have seen the SCR turning on is controllable, whereas it's turning off it's not controllable. And there is a requirement for turning on of the SCR, which are two requirements. That is, it should be in the forward blocking mode and the gate trigger should be applied. And both are unidirectional devices, power devices. All right. So that's all for lecture number 2. Thank you.